Welcome everyone to the fourth lecture of the course Statistical Model Selection for Stochastic Systems with applications to Bioinformatics, Linguistics and Neurobiology. My name is Guilherme. I am an assistant professor of the Institute of Mathematics of the Federal University of Janeiro. It's a pleasure to meet you and I hope you enjoy this lecture. In today's lecture, we are going to see an example of systems of stochastic chains with memory of variable length called GL neural networks. And as we'll see, an important parameter of these networks is what we call the interaction graph. And the main focus of this lecture is to present a very simple estimator of this interaction graph and also to study a few statistical properties of this estimator. And we will conclude this lecture by showing some simulations and also an application on real data set to illustrate the performance of this simple estimator. So let's begin discussing the GL neural networks. So in a GL neural network, we have D neurons. So here D is a positive integer larger than 1. And for this fixed D, we will denote D between the brackets as the set 1D. And this set denotes the set of neurons in the network. The time is going to be discrete and indexed by the set of integers, Z. And for each I, for each neuron in the network, and for each time t, we assign a random variable xi, t, or just xit, which either takes value 0 or value 1. And we say that xit is equal to 1 whenever the neuron I has a spike at time t. Okay? The configuration of the network at the time t is going to be a random vector xt, a d-dimensional random vector, where the coordinates are just x1t up to xdt. Okay? An important definition for us is what we call the path of the network up to the time t. So this is going to be denoted by x minus infinity t, and this is just the collection of all the random variables xis with I in the set 1D and S is at most t. Okay? And the collection xit with I in the set 1D and t in Z describes the GL neural network and is going to be denoted by x in boldface. Okay? So this is just a few notation that will be used throughout this lecture. To illustrate this notation, let us consider an example with D equals 4. So we have here on the x-axis the time and on the y-axis the neurons. So we have neuron 1, 2, 3, and 4. So let us suppose the time t is here. And in this case, the configuration of the network at this time is the vector 0, 1, 0, 0. So this is xt. And in particular, the second coordinate of this vector, which is x2t, is equal to 1. And the third coordinate of this vector, which is x3t, is equal to 0. And now, let's take another time t prime here. And in this case, the path of the network up to the time t prime is just the configuration of zeros and ones inside of this orange rectangle that I'm drawing on the screen. Okay, and is denoted by x minus infinity up to t prime. Okay, and now let's talk about the dynamics of the network. So the dynamics is as follows. At each time step, conditionally on the past, neurons update independently. So this means that for each time t and for each choice of symbols a1, ad in 0, 1, the probability that x1 t plus 1 is equal to a1, etc., xd t plus 1 is equal to ad, given the path of the network up to the time t. So this conditional probability is the product of I going from 1 to d of the probability that xi t plus 1 is equal to ai, given the path of the network up to the time t. And since these conditional probabilities are random variables, we ask to this identity to hold p almost steady. Moreover, the probability that the neuron I spikes at time t plus 1 is a function of its membrane potential. So this means that the probability that xi t plus 1 is equal to 1, given the path of the network up to the time t, so this is a function phi I of vit, and vit is what we call the membrane potential of neuron I at time t, and phi I here is what we call the spiking rate function of neuron I, and this is an increasing function of its argument. Okay? To complete the description of the dynamics of the model, I need to explain how to compute the membrane potential of neuron I at time t. So the membrane potential is VIT, and as you can see here, it's given by a sum over J going from I to D of W, J goes to I, times a sum over S, with S going from LIT plus 1 to T, of GJ of T minus S times XJS, where WJ goes to I is a real number describing the synaptic weight of neuron J on neuron I. LIT is the time of the last spike of neuron I before time t, and is defined as the sup over S is smaller or equal than t, such that xis is equal to 1. And the function gj is a positive function describing a postsynaptic current pulse. Before moving on, let me make two remarks. The first remark is the following. Whenever xit is equal to 1, meaning that neuron I spiked at time t, then the second sum appearing in the definition of VIT will be 0 for each j, and here we are using a convention that is sum over S going from t plus 1 to t of some function here is going to be 0 for each t. Okay? And then, since the second sum here is going to be 0 for each neuron j, we have that VIT is equals to 0 in this case. Okay? So, in other words, whenever the neuron spikes, its membrane potential is reset to 0. The second remark is the following. The time range in which we need to consider to compute VIT depends on LIT, which is a random quantity. So, in particular, the time range is not fixed. And so, in this sense, the random variable LIT introduces a variable structure memory in the model, very similar to what we observed in stochastic chains with memory of variable length. And so, in this sense, we can see GL neural networks as systems of interacting chains with memory of variable length. To illustrate these definitions, let us consider an example. Suppose I have neuron I here at time t plus 1, and suppose we want to compute what is the probability of neuron Y to spike at time t plus 1 given the past. To do so, the first thing we need to do is to compute the last time neuron I spiked before time t, which is here in this case. Okay? And as we saw in the definition of the model, the probability that neuron I spikes at time t plus 1 given the past depends on the past x through the configuration xjs with j in the set 1d minus I and s from time li t plus 1 up to time t, and this configuration here is what we call local pasts. Okay? So in this example, the local past used to compute the probability of neuron I to spike at time t plus 1 given this past is the configuration of zeros and ones inside this blue square that we call W. To conclude this example, let us compute the probability of neuron I to spike at time t plus 1 given this past. So let us denote this probability pi of 1 given W, because W is the corresponding local past. In this example, D is equals 4, and let us assume that here we have neuron 1, here neuron 2, here neuron 3, and in this case neuron I corresponds to the neuron 4. Okay? So in this case, the probability that neuron I spikes at time t plus 1 given this past is phi I of W 1 goes to I times G1 evaluated at 2, because the distance between this spike and time t is 2, plus W2 goes to I times G2 of 1, because the distance between this time and time t is 1, plus W3 goes to I times G3 of 3, because the distance between this spike and time t is equals to 3. So in this example, this is the probability of observing 1 given the local past W. In this lecture, we'll be considering GL neural networks which start from a given fixed past. To formalize this idea, let omega ADN be the set of admissible pasts, and the set is defined as the set of all space-time configurations zeros and ones in which the space component is the set 1D and the time component is the set of non-negative integers, such that for each I in 1D there exists Li is smaller or equal than 0 with xi Li equals to 1. Okay? Now observe that if the path of the network up to the time 0 is equal to little x, and the little x is an admissible path, then we can show that Li of 0 corresponding to this path will be strictly larger than minus infinity for all I in my set 1D, and in this case we can show that the sum over j going from 1 to d of wg goes to y times the sum of s going from Li of 0 plus 1 to 0 of j of minus s times xj s is finite for each I, and this implies that the probability that I1 is equal to 1 given that the path of the network up to the time 0 is 0x is well defined, so we can actually compute it. And then by induction, we can show that for each time t larger than or equal than 0, the probability that xi t plus 1 is equal to 1 given the corresponding path of the network up to the time t is also well defined. And since these conditional probabilities are well defined, for t larger or equal than 0, we can build the GL neural network step by step by using the fact that at each step, the neurons update independently. And so this guarantees the existence of the stochastic chain xt, that is the GL neural network, starting from the path x in the set of admissible paths. And in particular, observe that we do not assume that the GL neural network is stationary. So let us now discuss about the interaction graph of the GL neural networks and its estimation. So let us first define what we mean by the interaction graph. Okay? So neurons who have a direct influence on I are those belonging to the set Vi, which is the set of all neurons J, such that the weight W J equals to Y is different from 0. And so this set is what we call the interaction neighborhood of the neuron I. Okay? Note that the neurons in the interaction neighborhood Vi can be either excitatory, in this case W J equals to Y is positive, or the neuron can be inhibitory, and in this case the weight W J equals to Y is negative. Okay? And what is the interaction graph? So the interaction graph is a graph in which the set of vertices is the set 1D. So this is the set of vertices. And the set of edges are of the following form. So the set of edges are all the edges of the form ij, with j belonging to the interaction neighborhood of Vi. So this is the set of edges. Okay? And the goal of this lecture is to present a very simple estimator of the interaction neighborhood Vi of a fixed neuron I. And of course, I can estimate this interaction neighborhood for each neuron in my network, and by doing that, what I estimate at the end is the interaction graph. And of course, when we speak about an estimation problem, our knowledge about the parameter of interest, which is in this case the interaction neighborhood Vi, comes through a sample. So let me explain what do I mean by a sample. So imagine that we have a GL neural network with D larger or equal than 4, meaning that we have at least 4 neurons. And in this case, let's suppose that we have observed the activity of the neurons in a given set, F. So F here represents the set of these 4 neurons, and these 4 neurons have been observed during n time units. So imagine that's this time 1 and this is time n. Okay? And so in this case, this configuration here is what I mean by XF1. So this is the notation. And for instance, this last configuration here is XFN. Okay? And our sample can be thought as this matrix of zeros and ones where we have n columns and we have f cardinal of f, more precisely, rows. Okay? So this is the sample that we have access to. given the sample, we can now define what we call empirical probabilities. So recall that we have a given neuron I, which is fixed, and then for each given local past, I want to define what is the empirical probability of observing one given this local past. And this is done as follows. So we denote NIW, the number of occurrences of W in the sample. And similarly, I define NIW, 1, the number of occurrences of W followed by a spike of neuron I in the sample. Okay? Then I consider the set TNI, which is the set of all local paths appearing sufficiently many times in the sample, meaning that Ni of W has to be larger than n to the power xi plus 1/2, where the parameter xi belongs to the interval 0, 1/2. And finally, for each local past in this set Tin, we define what we call the empirical probability of observing a spike of neuron I given the local past, and this is denoted by p hat In of 1 given W, and this is defined as the ratio between NIW, 1 and Ni of W. Okay? And as we will see in a moment, in order to check whether the neuron K is or not in the interaction neighborhood Bi, we will compare the empirical probabilities for couples of tests that are identical outside K. And here on the screen, we have an example of a pair W and V, which are identical outside K. Okay? Because if I look at the raw corresponding to the neuron L, they have same configuration, but in the raw K, we don't say anything. They could be different, they could be equal. Okay? In the following, for each local path W in the set Tn, we denote TWKIN, the set of all local paths V, which are identical to W outside K, and we indicate this fact with this notation. Okay? And now, note that there is a very simple way of measuring the influence of neuron K on neuron I. So this can be done as follows. We can fix a threshold parameter epsilon, so it's a number between 0 and 1, and then I can take a couple of pair of local paths which are identical outside K, and then we can say that K is in fact influencing neuron I if the difference between the p hat In of 1 given W and p hat In of 1 given V is larger than this fixed threshold parameter epsilon. So this is a very simple way of saying that neuron K is in fact influencing neuron I. In this case, it seems natural to accept neuron K in the estimated interaction neighborhood. And just to repeat here with a picture, so imagine that I have a given local path W and another local path V, which are identical outside K, which can be very easily verified in this case. And also, let's assume that they are different with respect to the kth coordinate, which we can see this in the picture. And then in this case, if I compute the p hat of 1 given W minus p hat of 1 given V, and if this difference is larger than epsilon, then we'll say that K is in fact influence neuron I, and it's natural to accept K in the estimated interaction graph. Okay? In other words, to test the influence of k on I, we use the test statistics, which is delta ik, which is defined as the maximum over all local paths W in Tin, maximum over V, which is identical to W outside K, of the difference between the corresponding empirical probabilities. And if this quantity is larger than epsilon, then we accept that K is in the estimated interaction neighborhood. Okay? And this reasoning leads us to the interaction neighborhood estimator considered in this lecture. So how is it defined? So for any positive threshold parameter epsilon, the estimated interaction neighborhood of neuron I at accuracy epsilon, given the sample xf1 up to xfn, is defined as the set v hat epsilon in, which is the set of all neurons in f minus I, in which the test statistics delta inj is greater than epsilon. Okay? So this is the selection procedure that we use to estimate the interaction neighborhood of neuron I. To state the consistency of the estimator v hat, we need some assumptions. So the first assumption is the following. For all I in my network, the spiking rate function phi I is a C1 function, strictly increasing. The second assumption is the following. There exists P star in 0, 1/2, such that for all I in 1D and for all U real number, phi I of U is between P star and 1 minus P star. So this assumption ensures that the probability of observing a 1, no matter the path, will be always larger or equal than P star, and it will be at most 1 minus P star. And the third and last assumption is that we assume that Vi, so the interaction neighborhood, is contained in the set F, so in the set of observed neurons. Under the assumptions that we just described, we can prove the following, which is theorem 4.4 in the book. So the theorem says the following. Let xf1, xfn be a sample produced by the GL neural network satisfying the assumptions of the previous slide, starting from an indivisible path, little x. Then, for any epsilon n going to 0 as n goes to infinity, such that epsilon n is always larger or equal than c times n to the power psi over 2 for some constant c positive, where psi here is between 0 and 1/2 and is the parameter appearing in the definition of the set Tin. Okay? So under these conditions and with this choice of epsilon n, then we have that the estimator v hat, when we use the threshold parameter as epsilon n, is equal to Vi eventually almost surely. Okay? In other words, our estimator is consistent. So this result could also be extended to the case when Vi is not contained in the set of observed neurons F. This won't be discussed in this lecture, and you can find the details in the book. So let us make some remarks. First of all, we are not estimating the weights of the interaction, only the existence or not of interactions. So in this sense, we are estimating an oriented graph which is not weighted. Moreover, our procedure is quite general and may be applied to many other settings. And finally, we can deal with the case in which the system has several invariant states. Now let us discuss some application on simulations and also on real data. Okay? So in the remaining part of this lecture, we proceed as follows. First, we will show some simulation to explore the parameters epsilon and psi, and then we will discuss briefly a procedure to deal with small sample sizes, and then we will conclude this lecture by showing some results of real data analysis. Okay? In this picture, we have several 5x5 matrices corresponding to the interaction graphs obtained by applying the interaction neighborhood estimator for each one of the 5 neurons in the network for different values of the parameters psi and epsilon. In all cases, the n is 10 to the power 6, and when we move to the right, we increase the value of the parameter psi, and when we move downward, we increase the value for the parameter epsilon. Okay? So let's have a look at this particular matrix. Okay? Here, in all cases, we have 5 neurons, right? So let's say it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And here, each entry is either white or black. The white entries are correct absent connections, and the black ones are correct present connections. In this example, the value of epsilon is 0.05 and psi is 0.001. As you can see, for this choice, the estimator perfectly estimates the true interaction graph. Now, let's have a look at this particular matrix. Okay? So here we have white and black entries as before, but also entries with 3 different colors. The hatched white color indicates a false negative. The dark gray color indicates an inconclusive existent connection. And a light gray color indicates an inconclusive non-existent connection. We say that a connection J goes to Y is inconclusive if we cannot find in the sample 2 pairs of local paths V and W which are identical outside J and appear sufficiently often. So we cannot actually compute our estimator in this case. As expected, the number of inconclusive connections increase with the parameter psi, and the number of false negative increases with epsilon. Finally, let's have a look at this particular matrix. Here we have black and white entries as before, but also hatched gray entries. These entries indicate false positive connections. As you can see, the number of false positive connections increases as the value of the parameter epsilon decreases, which is expected. To sum up, although the estimator V hat is consistent, its performance for finite sample sizes depends heavily on the choice of the parameters epsilon and psi. As we just saw, this simple interaction graph estimator has a major limitation, namely, whenever the sample size is small or the number of observed neurons is large, there will be too many inconclusive connections. And to deal with this issue, we propose to use the interaction graph estimator together with a pruning procedure. In a few words, what we do is to re-estimate the interaction graph is considering neurons that the original estimator says is not pre-synaptic. So all the neurons J that the original estimator says W, J goes to Y, is 0, are disconsidered, and then we apply our interaction graph estimator for this reduced network. And by doing that, we reduce significantly the number of inconclusive connections, as we'll see in the next slide. And very interestingly, this iterative pruning procedure conserves the consistency of the estimation. In this picture, we have two 10 by 10 matrices, where the first one corresponds to the interaction graph obtained by applying the interaction neighborhood estimator for each one of the 10 neurons in the network without pruning. So we say before pruning. The second matrix corresponds to the interaction graph obtained by applying the iterative pruning procedure. So here we see after pruning. Okay? In both cases, we have used the same parameters psi and epsilon. And as you can see, the iterative pruning procedure reduces significantly the number of inconclusive connections. Okay? To conclude this lecture, we present results on a real data set of 5 neurons of the antenna lobe of the Schistocerca americana, which is the insect that you see on the screen. And the antenna lobe is important because it's the primary olfactory brain area in insects. The corresponding value for n in this data set is 18. So n is equal to 18 times 10 to the power 4. And we apply the interaction graph estimator with xi equals to 0.001 and epsilon equals to 0.5. Okay? With these values of psi and epsilon, and for a value of n equals to 10 to the power 6, if the network was generated by a GL network, we would recover exactly the through interaction graph as we saw on the simulations. Okay, so this justifies our choice for psi and epsilon. The results are the following. On the 5 by 5 matrix on the left, the results correspond to the whole data set. We can see that the interaction neighborhood estimator indicates that neuron 1 is in the interaction neighborhood of neuron 2, and similarly that neuron 2 is in the interaction neighborhood of neuron 1. We can also see that the interaction neighborhood estimator indicates that neuron 3 does not belong to neither the interaction graph of neuron 1 nor to the interaction graph of neuron 2. Note that the results are mostly inconclusive for neurons 4 and 5, even with the iterative pruning procedure. In order to validate this estimation procedure, we split the dataset in 2 parts and apply the interaction graph estimator for each part. The results for the first and second half are shown in the 5 by 5 matrix on the middle and on the right, respectively. We can see that the estimator procedure gives us the same results for the 2 different parts of the dataset, and they are compatible with the results on the whole dataset, indicating that the results are robust to data splitting for this dataset. Okay? To sum up, in this lecture we have defined the GL neural networks, we have seen how to estimate the interaction graph of these networks, and we have seen applications of this estimator on real data set and on simulations as well. I hope you enjoy this lecture.